An idle power plant floor carries a silence more oppressive than any sound. As a 40-ton steam turbine remains inert, the quiet isn't merely heard, the financial bleeding is physically felt. $58,000 were being lost each day. The livelihoods of 400 people were in jeopardy, all dependent on a contract deadline that refused to budge. The manufacturer's diagnostic specialists had already put away their vibration analysis equipment. Their conclusion was unwavering: a complete loss. They gestured at the digital evidence, at the crimson lines on their monitors that signaled a disintegrated core. Their focus was on the pixels when it should have been on the steel itself. To grasp why their assessment was flawed, one must first appreciate the nature of this machine. It is more than a mere catalog entry or an item on an asset ledger. It stands as a testament to a particular chapter in mechanical history, a 12-stage reaction steam turbine, constructed in an age when engineering valued endurance over built-in obsolescence. It rests in the hall's center like a dormant titan, a colossal structure of high-alloy chromium-molybdenum steel with rotors machined to spin at a precise 3,600 revolutions per minute. At such a velocity, the gaps between the spinning blades and the fixed casing are measured in microns, mere fractions of a human hair. Within that casing, during operation, superheated steam at 900 degrees Fahrenheit impacts the initial stage nozzles at supersonic speeds. This process is a controlled and violent chaos that demands unwavering mechanical perfection to be maintained. For 40,000 hours of service, this particular unit had operated without a single significant failure. It served as the very pulse of the regional power grid, a dependable titan that transformed thermal energy into megawatts with a steady rhythm that its operators had begun to see as a given. It had endured load rejections, fluctuations in the grid, and emergency shutdowns. The machine had a story. Yet, a story does not register on a digital diagnostic summary. Up until that week, its bearings had sustained an ideal oil wedge, and its vibration levels were almost non-existent. Now, it was inert. And an inert turbine is a machine in its death throes. The thermal shrinkage alone alters the fit of every seal and bearing, creating a risk of the rotor bowing under gravity if not kept on a turning gear. The financial fallout from this stillness was immense. The consequences could be tracked from the control center, along the transmission lines, and into the local factories that depended on this continuous power supply for their own operations. Supply chains were beginning to fail. The local utility had to purchase emergency power at exorbitant prices simply to maintain electricity in the town. With every hour the turbine was inactive, the quarter's profit margin dwindled. Within this field, forced outages due to vibration are responsible for almost 40% of all downtime, a figure that typically culminates in a board of directors seeking someone to hold accountable. The plant manager felt the gravity of the situation. He was contemplating a $7 million asset that had devolved into a $7 million paperweight, confronting the potentially career-ending choice to scrap it based entirely on the word of technicians who placed more faith in software than in their own senses. A core distinction exists between digital health and mechanical integrity, a difference frequently overlooked in contemporary industrial maintenance. Digital health is the information a sensor provides based on voltage settings, resistance measurements, and pre-programmed algorithms. It offers a binary view of a multifaceted analog world, perceiving things in terms of ones and zeros, pass or fail. Mechanical integrity, however, represents the tangible truth of the metal itself. It is found in the wear on a journal bearing, the exact viscosity of the lubricating oil, the resonant frequency of a casing under strain. It is the very texture of the machine. The manufacturer's personnel perceived a digital apparition, a proportional drift in the vibration readings that their manual equated with a disintegrated core. They did not take the time to open the casing for a visual confirmation. They did not take the time to inspect the oil filters for the telltale shimmer of metal particles that invariably accompanies a core failure. They put their faith in the code. They viewed the machine as a malfunctioning computer accessory, not as a physical system in distress. The plant manager felt, on a gut level, that the diagnosis was incorrect. A turbine does not simply fracture its core without a powerful physical incident, a crash that would rattle the foundations and be detected by seismographs. This machine had merely tripped off the line and then would not restart. Yet, when faced with a group of clean room specialists armed with six-figure diagnostic equipment, it becomes difficult to rely on one's intuition. It is challenging to contest a graph that declares catastrophic failure. Consequently, the choice was nearly finalized. The scrap dealers were being contacted. The order for a replacement, an expensive $2.4 million with a 6-month delivery time, was on his desk, awaiting his signature. This was the prevailing mood when a call was placed to an outside specialist. The experts had delivered their judgment, but the machine itself had yet to be truly examined. The appearance of the manufacturer's response team created a stark juxtaposition. 3 men, attired as if for work in a semiconductor fabrication plant, entered the gritty, ozone-tinged temple of heavy machinery. They sported immaculate white hard hats that had clearly never seen a falling object, and high-visibility vests that were crisp and new. These were the clean room technicians, the official representatives of the original equipment manufacturer, and they moved with the aloof air of high priests on a visit to a provincial church. They carried no toolboxes, no cleaning cloths, no crowbars. Instead, they brought pelican cases padded with shock-resistant foam, which held laptops that were more expensive than an average operator's yearly wage. They strode past the silent turbine, not even sparing a look at its casing, their focus locked on the climate-controlled haven of the control room. In their view, the physical machine was merely a messy, cumbersome accessory. The true reality was in the data it produced. Their gear was a clear indication of a strategy that prioritized quantifying a problem over actually comprehending it. With military-like efficiency, they unpacked $50,000 multi-channel analyzers and connected them to the plant's Bentley, Nevada monitoring system. These spectral analysis instruments measured shaft displacement 20,000 times per second, breaking down vibration signals into intricate Fourier transforms. It was a technology crafted to reduce diagnostics to a purely objective science. After launching their exclusive software scripts, they did what no true mechanic ever does. They stepped back, folded their arms, and waited for a screen to reveal the truth. The procedure was excruciatingly protracted. Loading bars inched their way across high-definition screens. The technicians conversed quietly about signal-to-noise ratios and bandwidth filters, paying no mind to the plant manager who paced behind them, watching his budget drain away with each passing moment. At last, the head technician, a man who probably knew more about software design than about the rotor's metallurgy, turned. He did not look at the turbine, but at the manager. "It's finished," he declared. The judgment was pronounced with the detached manner of a medical examiner. A catastrophic failure of the core. He indicated a graph where a red line veered dramatically from the baseline. The diagnosis was attributed to a particular alarming anomaly: proportional drift. In the clinical terminology of their manual, proportional drift signified that the correlation between the shaft's center line and the sensor's voltage output had lost its linearity. The sensors were detecting a displacement that should not be possible. As per their diagnostic flowchart, if the probes registered this specific voltage discrepancy, it meant the rotor shaft had lost its structural integrity. This implied that the huge steel shaft, with a weight comparable to a fully loaded semi-trailer, was deforming under its own mass. It suggested the blades had likely made contact with the casing, ruining their aerodynamic properties and destroying the turbine stages. It was, in effect, a death sentence. This is the particular hubris of the contemporary method. When the sensor indicates a machine is broken, they cease to examine the actual metal. They saw no need to open an inspection hatch. They did not take an oil sample to search for the shimmer of Babbitt metal or steel fragments that would certainly be present if a rotor had truly ground itself apart. A shattered core is a violent occurrence. It generates debris, intense heat, and physical damage. Yet, the oil was unadulterated. The casing remained cool. The only location where the turbine was demolished was within the simulation on their laptop. However, when the manager inquired about the absence of debris, they simply pointed at the screen. The sensor doesn't deceive, they maintained. The drift is undeniable. Their recommended course of action was the direct outcome of their diagnosis, a complete replacement of the core. They outlined the schedule without any consideration for the operational disruption. A new rotor would need to be forged, machined, and balanced at their factory in Germany. The lead time was 6 months. The cost was $2.4 million, not including installation or the rental of a heavy lift crane to take off the building's roof. They were sentencing the plant to 6 months of inactivity and financial collapse, all based on a voltage measurement. The plant manager reviewed the proposal and then glanced at the silent machine. He felt the sickening certainty of a mistake being made deep in his gut. The reasoning was flawless, yet the conclusion felt entirely wrong. A machine of this kind does not die silently if it breaks apart. He excused himself, stepped out to the loading bay away from the white hard hats, and made a call he was not supposed to make. He did not contact another consulting company. He dialed a number scrawled in grease pencil on an old logbook, reaching out to an independent specialist who lacked a corporate backing, a clean room uniform, and a belief in screens. To grasp how a group of highly compensated experts could stand before a completely repairable machine and sentence it to be scrapped, you must comprehend the inherent flaw in modern industrial diagnostics. We have reached a point where we place more faith in the map than in the actual landscape. The breakdown in this situation was not within the turbine's steel. It was in the mindset of those performing the diagnosis. Contemporary diagnostic equipment is exceptional at determining what is occurring: the voltage, the temperature, the vibration level. However, it is woefully inadequate at explaining why. In the space between the what and the why, a loss of $7 million can occur. The corporate group was depending on non-contact eddy current probes. These are complex sensors threaded into the bearing housing that create a magnetic field to gauge the distance to the rotating shaft. They translate that distance into a voltage. As the shaft nears the probe, the voltage decreases. As it moves away, the voltage increases. The software processes this voltage through a correlation algorithm and then reports on the machine's condition. Yet, there lies a critical weakness. The sensor itself is unintelligent. It is unaware of the reason for the voltage change. It only registers that the gap has altered. If the shaft physically shifts due to a collapsed bearing, the voltage will change. But if the bracket securing the sensor bends from heat, or if the sensor itself vibrates at a particular frequency, the voltage will also change. The computer is incapable of distinguishing between these scenarios. It detects a voltage shift, consults its internal reference table, and signals core failure. This effect is referred to as sensor drift, or, more perilously, ghost codes. It is a persistent issue in modern control systems. We have engineered machines with such sensitivity that they can detect their own imagined problems. The software is designed with a safety-first approach. It defaults to the most severe possibility to safeguard the equipment. If a reading is unclear, the logic presumes the shaft is violently oscillating. It does not stop to think that perhaps, just perhaps, the sensor is providing false information. This leads to a cycle of confirmation bias. The technician observes the core failure alert, and because the alert is specific and seemingly authoritative, they cease to investigate other potential issues. They shift from thinking like engineers to behaving like parts swappers. The parts swapper mindset is the adversary of genuine problem solving. A parts swapper sees a machine as an assembly of interchangeable modules, and if a module shows an issue, it should be replaced. They do not search for the fundamental cause, they search for the defective component. In this instance, the code indicated the rotor was at fault. Therefore, their logical step was to replace the rotor. A true troubleshooter, in contrast, reasons backward from the physical principles. They pose the difficult questions that the software overlooks. The particular failure mode the corporate team had decided upon was a fractured blade in the low-pressure section. Their hypothesis was that a blade had broken off at its base, leading to a significant imbalance that caused the shaft to wobble, which in turn caused the drift in the sensor data. On a computer screen, this theory is perfectly logical. The calculations support it. However, in the tangible world, it presented a contradiction that should have been glaringly obvious to anyone who had ever been near a turbine in distress. When a blade breaks at 3,600 RPM, it is not a quiet affair. It is akin to a grenade detonating inside a steel container. The kinetic force of a detached blade is sufficient to pierce the casing. At the very least, it results in a deafening, grinding crash as the imbalanced rotor smashes against the stationary seals. This creates friction, which in turn generates massive immediate spikes in temperature. It transforms the oil into a glittering concoction of shredded metal. Yet this turbine had shut down quietly. The bearing temperatures remained normal right up to the moment it tripped. The oil was clean. The casing was undamaged. There was a digital diagnosis of a violent, catastrophic event and a physical reality of a machine that had simply ceased to operate. The corporate team was requesting the plant manager to trust the screen over his own senses. They were asking him to accept that a 40-ton rotor had self-destructed without a single sound. They were so captivated by the complexity of their instruments that they were unable to recognize the impossibility of their own conclusion. They were prepared to rip out the plant's core because a voltage reading had deviated by 3% from its specification. This is the peril of high-tech naivety. It fosters a reality where the simulation takes precedence over the physical world. The plant required someone who was not concerned with the simulation. It needed someone who would bypass the control room, disregard the flashing red screens, and place their hand on the cool steel of the casing. It needed the institutional specialist. By the time the independent specialist showed up, the sun was already dipping on the 4th day of the shutdown, drawing long, inert shadows over the cooling towers. He did not arrive in a company-branded sedan with a corporate emblem on its side. He came in a truck that appeared to have logged as many service hours as the turbine itself, a vehicle that was clearly maintained rather than replaced. As he stepped onto the gravel, the difference between him and the manufacturer's team was stark and total. There were no pristine white hard hats, no high-visibility vests that were stiff from being new. He was dressed in coveralls that had been laundered countless times, the material softened and marked with the remnants of other machines, a unique stain of grease and high-pressure steam that never fully washes out. He had not brought a crew. There were no aides to haul cables, no junior technicians to assemble tripods. He carried a single, heavy leather tool bag that resembled something a country doctor might have used in the 1950s. Inside, there were no laptops, no spectral analyzers, no USB connections. There was a set of gleaming wrenches, a dial indicator, a flashlight with a gentle incandescent glow, and a mechanical stethoscope. This was a collection of tools for listening, not for data processing. He passed through the security gate with the measured, purposeful stride of a man who bills for the solution, not for the time spent. The tension in the control room when he walked in was so thick it could have stalled a compressor. The plant manager had the look of a condemned man meeting his lawyer for the last time, frantic, perspiring, and clinging to a sliver of desperate hope. The corporate technicians, clustered around their luminous monitors, barely glanced his way. When they did, it was with an expression of poorly hidden amusement. To them, this was a ridiculous spectacle. They possessed the data, the proprietary algorithms, and the definitive conclusion. To bring in a grease monkey to challenge $1 million diagnostic system was, in their view, an act of foolish desperation. One of them even smirked, tapping his pen on a printout of the proportional drift graph, as if to say, "The numbers are the numbers, old-timer." The specialist paid no mind to the smirk. He did not even look at the screens. He went directly to the plant manager, shook his hand, and asked a single question. "Is the system locked down, or do we have permission to rotate it?" The manager faltered, explaining that the system was tripped and locked by its safety protocols. The specialist simply nodded, then turned his back on the air-conditioned comfort of the control room. He had no interest in seeing the simulation. He opened the heavy steel door to the turbine deck, leaving the cool, purified air for the humid, ozone-scented environment of the plant floor. The quiet on the turbine deck was a tangible thing. Normally, this area is a deafening roar of steam and machinery, a place where the very air seems to shake. Now, it was like a mausoleum. The specialist strode the length of the machine, his bootsteps echoing on the diamond plate walkway. He treated the turbine not as a piece of industrial hardware, but as a living creature in a state of suspended animation. He laid a hand on the high-pressure casing. It was still warm, emitting the deep, residual heat of a massive steel casting. He shut his eyes, sensing the thermal variations beneath his palm. He was not just checking the temperature, he was feeling for the tension in the metal, the slight distortions that occur as a machine cools unevenly. He proceeded to the bearing housings, clearing a film of dust from the sight glass. He opened a sample valve on the return line, allowing a few drops of oil to fall onto his fingers. He rubbed the liquid, checking for the distinct grit of a core failure. the minute traces of aluminum oxide or bauxite that show up when a rotor begins to consume its own housing. The corporate team had relied on a spectral analysis. He was searching for physical proof. The oil was slick. It was unadulterated. It lacked the gritty texture of contamination. He sniffed it. It had the smell of heated synthetic hydrocarbons, but not of burning. There was no sharp odor of scorched Babbitt metal. He eventually came back to the control room window, where the corporate team observed him as if he were an animal in a zoo. He signaled for the manager to join him outside. When the manager came through the door, the specialist pointed to the colossal, silent machine. "Your experts claim the core is destroyed," he stated, his voice deep and raspy, slicing through the low hum of the auxiliary equipment. "But a destroyed core makes a lot of noise when it fails. It leaves behind debris. It scorches the oil. This machine didn't fail violently. It just shut down." He cleaned his hands on a cloth. "The information on those screens is a picture of a phantom. It reveals the symptom, not the source. We're going to start it up." The manager's face went white. To start a turbine that has been diagnosed with a shattered core is, by all technical standards, madness. If the experts were correct, the machine would tear itself to shreds. The specialist noticed the fear. "Have faith in the metal," he advised, "not in the map." The specialist walked away from the huge, silent casing of the primary turbine and went down the narrow metal steps to the plant's basement. This area is the machine's underbelly, a complex labyrinth of pipes, auxiliary systems, and high-voltage cables that power the equipment above. The corporate technicians did not go down with him. For them, the act of overriding safety protocols to initiate a manual startup is a momentous occasion in industrial engineering. It signifies a point of no return. The plant manager's hand lingered over the human-machine interface, his fingers shaking slightly above the Initiate button. Behind him, the manufacturer's representatives had literally moved to the far end of the control room, placing a solid barrier of reinforced glass and concrete between themselves and the turbine. Their action was a clear declaration. "We do not support this. If this rotor shatters and sends debris through the roof, we will not be held responsible." They had their phones out, recording their dissent, constructing a legal defense. The specialist stood by himself on the turbine deck, wearing hearing protection, with his stethoscope hanging around his neck like a lucky charm. He gave a single, sharp nod towards the glass window. "Go ahead." The manager activated the command. The startup began with the groan of the turning gear releasing, quickly followed by the profound, earth-shaking shudder of steam entering the high-pressure nozzles. 40 tons of finely engineered steel started to break free from the hold of static friction. The floor plates vibrated under their feet. On the control room monitors, the RPM display changed from 0 to 10, then 20, gradually increasing as the steam valves began to open. At 100 RPM, the machine was merely warming up. The sounds were deep, steady, and mechanical, the usual clatter of a dormant giant coming to life. The corporate technicians watched their vibration monitors with intense focus, anticipating the red line, waiting for the proportional drift to surge and validate their diagnosis. They were expecting a crash. They were expecting the violent, chaotic grinding of a shattered core tearing itself apart. But as the turbine surpassed 500 RPM and neared its first critical speed, the expected crash never occurred. Instead, something different began to happen. It began as a faint whine, almost inaudible above the sound of the steam, but as the speed increased, it intensified into a sharp, distinct note. It was not the sound of mechanical failure, like gravel in a blender. It was a clear, high-frequency tone, a harmonic that seemed to vibrate directly in the teeth of anyone nearby. It was like the sound of a wet finger tracing the edge of a crystal glass, but magnified to the volume of a jet engine. In the control room, the monitors displayed confusingly normal readings. Their software was programmed to detect low-frequency thumping, the characteristic sign of a heavy, unstable rotor. They had configured their low-pass filters to disregard anything above the fifth harmonic. But the scream was occurring at a much higher frequency, precisely at the 19th harmonic, a well-known frequency that can cause circuit breakers to trip and confuse digital systems. The algorithm dismissed it as unimportant noise. On the deck, the situation was alarming. The sound was tangible. It was a singing vibration that caused the handrails to hum. The specialist did not back away. He moved closer. He walked directly to the number 2 bearing housing, the source of the noise. He closed his eyes, shutting out the visual distraction of the spinning coupling, and placed the metal probe of his stethoscope against the cast iron housing. He listened. To an inexperienced ear, it was simply noise. To him, it was valuable information. He could hear the rotor spinning smoothly and correctly. There was no heavy, rhythmic thumping of a broken blade. The core was undamaged. The scream was not originating from the shaft itself. It was layered on top of it. It was a resonance. The machine was not failing. It was vibrating in response to something else. It was a harmonic signal of distress. He moved the stethoscope probe, following the sound like a doctor searching for a heart murmur. He went from the bearing casing to the hydraulic supply lines. The sound grew louder. He moved to the governor control block. Louder still. The scream was not coming from the bearing. It was being transmitted into the bearing. The massive steel housing was functioning like a speaker, amplifying a vibration that was starting in the control system. The corporate technicians saw him there, hand on the screaming machine, and they waved frantically for the manager to activate the emergency trip. They saw a man endangering his life next to a potential bomb. But the specialist opened his eyes and looked up at the control room. He did not signal to shut off the power. He signaled to maintain the speed. He had located the phantom. It was not a shattered rotor. It was a frequency. The machine was screaming because it was in conflict with its own control system. To comprehend the events within that casing, one must grasp the physics of a phantom. In the domain of heavy industrial equipment, resonance acts as an unseen destroyer. It is the process by which energy discovers a favored rhythm and magnifies it to the point of destruction. Every object possesses a natural frequency, a particular pitch at which it prefers to vibrate. This is demonstrated by the classic example of an opera singer breaking a wine glass. The singer produces the exact note that corresponds to the glass's natural frequency, causing the energy to build up with each wave until the structure fails. However, in a steam turbine, the glass is a cast steel bearing housing that weighs 3,000 pounds, and the singer can be something as small and seemingly trivial as a hydraulic valve. The corporate team had been searching for a mechanical cause of the vibration: a bent shaft, a missing blade, a loose coupling. These are substantial low-frequency occurrences that can shake the entire floor. But what the specialist was detecting through his stethoscope was a high-frequency hydraulic flutter that had precisely matched the resonant note of the bearing pedestal. The source of the problem was not the massive rotor. It was not the millions of dollars worth of precision steel spinning at 3,600 RPM. It was a component no larger than a soda can, located deep within the auxiliary rack, a proportional control valve in the governor system. This valve functions as the brain of the hydraulic system, taking electrical signals from the control room and translating them into oil pressure to operate the massive steam valves. It is designed to be precise, smooth, and silent. But this particular valve was hunting. Hunting is a term used by engineers when a control loop becomes unstable. The computer instructs the valve to open to 50%. The valve, possibly due to a tiny piece of debris or a slight calibration error, opens to 51%. The computer detects the error and signals, "Too much, reverse." The valve then closes to 49%. The computer signals, "Too little, open more." This back and forth between the digital controller and the mechanical valve occurs hundreds of times per second. The valve spool starts to oscillate, vibrating violently. This is where the physics become fascinating, and where the corporate diagnosis completely missed the mark. Hydraulic fluid is, for all intents and purposes, incompressible. It is as rigid as steel. When that valve oscillated back and forth 200 times a second, it was not just moving oil. It was sending high-pressure shock waves through the stainless steel tubing. These shock waves propagated at the speed of sound through the fluid, striking the hydraulic actuators mounted on the turbine's bearing housing. The bearing housing was being subjected to a hydraulic jackhammer, 200 times per second. The vibration was minuscule in terms of displacement, but immense in terms of energy. And this is where the total loss diagnosis originated. The non-contact probes that the corporate team depended on measure the gap between the probe tip, mounted on the housing, and the shaft. When the hydraulic shock waves vibrated the housing, the probe vibrated with it. The probe detected the rapidly changing gap and misinterpreted it as the shaft violently oscillating. The computer registered the changing gap, but more crucially, the vibration was distorting the zero crossings of the sensor's sine wave. The safety logic, calibrated for 60 Hz, could not process the additional noise. It saw the distorted signal, assumed the shaft was bouncing erratically, and matched the amplitude to the shattered core profile. A shattered core vibrates at 1x or 2x the running speed, 60 or 120 Hz. This vibration was screaming at a much higher frequency, a harmonic that the standard filters dismissed as background noise. The specialist removed the stethoscope from his ears and returned to the control room. The manager was looking at him, his hand still poised near the trip button. The corporate technicians were silent, anticipating an explosion. The specialist did not appear frightened. He seemed irritated. "She's not failing," he stated, his voice even and calm. "She's screaming because she can't regulate herself. You have a governor valve hunting at 200 Hz. It's vibrating the sensors, not the shaft." He pointed to the alarming red line on the screen. "That isn't a death rattle. That's a feedback loop." He had identified in 5 minutes with his ears what a $50,000 computer had misinterpreted for 4 days. The machine was not broken. It was just agitated. The solution proposed by the manufacturer would have been a display of industrial brute force. To replace the core, they would have needed to bring in a 400-ton crane, create an opening in the facility's roof, and take apart the turbine casing piece by piece, a procedure that would have taken weeks just to begin. It was a crude method for a problem that needed a delicate touch. The specialist solution, in stark contrast, was almost laughably simple. He did not request a crane. He did not request a team of welders. He asked for a small, insulated, flathead screwdriver and a multimeter. He went back down to the basement, to the hydraulic power unit that supplied the governor system. This was the center of the control loop, a unit with pumps, filters, and accumulators that hummed with the pressure of 2,000 psi fire-resistant fluid. The cleanroom technicians stayed upstairs, observing the monitors, certain they were watching a deluded old man meddling with a dead machine. They had already composed the machine's obituary. They were merely waiting for the post-mortem. The specialist found the control cabinet for the governor valves. He opened the panel, exposing a set of analog amplifier cards. These cards act as translators in the machine world. They receive digital commands from the control room and change them into the electrical current that operates the hydraulic coils. They are straightforward, durable, and fully adjustable, if you have the right knowledge. The corporate team had overlooked them because the cards were not indicating any faults. The green lights were on. In a digital diagnosis, green signifies that everything is fine. To an analog specialist, green simply means the fuse is intact. He connected his multimeter leads to the test points on the card that controlled the number 2 governor valve. The voltage on the display was fluctuating wildly, jumping up and down by half a volt. This was the electrical sign of the hunting. The valve was acting erratically, desperately trying to find a position it could not maintain, propelled by a control loop that was overly aggressive. The gain, the sensitivity of the valve's reaction, was set too high. It was like a driver oversteering on a slippery road. Each small adjustment led to a bigger mistake, pushing the system into a violent oscillation. The solution was not a $2.4 million rotor. It was a 3mm turn of a potentiometer labeled gain. With the unwavering precision of a bomb disposal expert, the specialist placed his screwdriver into the tiny brass slot of the potentiometer. He did not simply turn it, he felt it. He observed the multimeter, but more importantly, he listened to the hydraulic lines running overhead. He rotated the screw counterclockwise, decreasing the circuit's sensitivity. It was a minute adjustment, perhaps only 5 degrees of rotation. The result was immediate. The frantic flickering on the multimeter slowed, then stabilized into a constant, unwavering voltage. The high-pitched whine from the hydraulic lines, the precursor to the scream, disappeared. The valve ceased its struggle with the computer and settled into its designated position. The system had transitioned from a state of frantic resonance to one of calm stability. He had not replaced a single piece of steel. He had simply re-established the communication between the electronics and the mechanics. He went to the hydraulic lines and placed his hand on the stainless steel tubing. Previously, it had been vibrating with a rapid, high-frequency tremor. Now, it was completely still, pulsing gently with the steady flow from the pump. The stiffness had been restored to the system. The fluid was no longer a jackhammer. It was a liquid solid, holding the valve precisely where it should be. Upstairs in the control room, the reaction was one of confusion, verging on alarm. The red line on the vibration monitor, the line that had condemned the machine to death, did not just decrease, it plummeted. It went completely flat. The lead technician tapped his screen, thinking the sensor had finally failed altogether. He checked the cable connections. He restarted the software. He could not comprehend that the catastrophic core failure had just been resolved by a man in the basement with a screwdriver. The specialist shut the cabinet door and wiped a smudge of grease from the handle. He put his multimeter back in his leather bag. There was no fanfare, no celebratory gestures. This was not a miracle to him. It was simply a calibration. He had saved the company $7 million and 6 months of lost production in less than 30 minutes, not by adding anything new, but by eliminating the noise. He walked back up the stairs to the turbine deck, where the silence was no longer oppressive. It was filled with anticipation. The phantom was gone. The machine was prepared to operate. The specialist re-entered the control room and wiped a trace of hydraulic fluid from his thumb. The atmosphere in the room was no longer thick with apprehension. It was now fragile with bewilderment. The red lines on the monitors were gone, replaced by flat green indicators showing a machine at rest. The corporate team gazed at the data, anticipating the return of the anomaly, certain that a minor adjustment to a potentiometer could not possibly fix a catastrophic core failure. The specialist ignored them. He addressed the plant manager. "Start her up," he instructed. "Full speed, 3,600. The manager paused for a moment, his gaze shifting to the corporate lead, who stood with his arms folded, shaking his head in silent disagreement. Then, the manager turned to the operator and gave a nod. The command was given. "Initiate start sequence." The floor beneath them vibrated as the main steam stop valves opened. The RPM counter started to rise. This is the decisive moment for any rotating equipment. As a turbine accelerates, it must navigate its critical speeds, specific RPM ranges where the rotor's natural frequency aligns with its rotational speed. If the shaft is bent, or if the core is genuinely fractured, the vibration at these critical speeds becomes intense enough to break bolts. It is the test that distinguishes a healthy machine from a failing one. 1,000 RPM. The control room was completely silent. The corporate technicians were monitoring the vibration amplitude, awaiting the exponential surge that would signal destruction. 1,500 RPM, the first critical speed. The floor produced a gentle, rhythmic hum that resonated through the soles of their shoes. It was the normal, healthy resonance of 40 tons of steel centering itself. The vibration monitors showed a flicker, 0.8 mils, 0.9 mils, before settling back down. All green. 2,000 RPM. The scream was supposed to begin at this point. This was the frequency at which the hydraulic valve had been hunting, causing the bearing housing to panic. But the room was filled only with the growing roar of the turbine. The high-pitched, piercing whine had vanished. The bearing housing was no longer acting as a speaker. It was simply a piece of iron performing its function. The specialist observed the corporate team. He saw the understanding dawn on them. They were not witnessing a disaster. They were witnessing a masterclass. 3,000 RPM. The machine was now emitting a clean, powerful tone that could be felt in one's chest. The vibration readings were remarkably low, 0.4 mils, better than the factory specifications. The rotor, which they had asserted was bent and shattered, was spinning with the precision of a gyroscope. 3,600 RPM, synchronization speed. The operator, now grinning, looked at the specialist. "Ready to sync?" The specialist nodded. The breaker closed with a solid, metallic clap that resonated from the switchgear room. The generator connected to the grid. The amperage began to rise. 10 megawatts, 50 megawatts, 100 megawatts. The total loss was now supplying power to the entire county. The corporate team started to pack their equipment in silence. There were no apologies. They shut their laptops and wound up their cables with the rigid, awkward motions of men who had been thoroughly humbled by physics. The lead technician stopped at the door, looking at the specialist. The data indicated a drift, he maintained, clinging to his digital version of reality. The data showed what the sensor was experiencing, the specialist answered, his voice low. But you didn't investigate what was making the sensor vibrate. You trusted the screen, so you stopped paying attention to the machine. The plant manager accompanied the specialist to the loading dock. He glanced at the invoice the specialist had written on a notepad. The amount was a tiny fraction of the cost of a new rotor, a tiny fraction of the cost of the downtime. We were on the verge of scrapping it, the manager said, looking at the steam billowing from the cooling towers, the plant vibrant with activity again. We were about to discard it all. Machines are meant to operate, the specialist remarked, tossing his tool bag into his truck. It's usually the people who cause the problems. We are in an age that venerates data, but has lost the skill to interpret it. We have created sensors capable of detecting a micron of movement, yet we have lost the capacity to comprehend why that movement occurred. That turbine is operational today, not because of a software update, but because someone recalled that engineering is a physical science, not a digital fantasy. If you wish to understand the language of the machines that power our world, subscribe to the channel. We repair the things that the experts cannot.